Okay, so now that we've reminded ourselves what the adjective Hermitian means, let's turn to the statement of the spectral theorem. The spectral theorem comes in 3 parts, and I'm going to state these parts separately and release separate videos for them so that you can reference them individually. So, what does the first part of the spectral theorem say? The first part of the spectral theorem says that the eigenvalues of any Hermitian matrix are guaranteed to be real numbers. So the first part of the spectral theorem says that the eigenvalues of every Hermitian matrix are guaranteed to be real numbers. This is already a significant statement because we've already seen examples previously of matrices that had eigenvalues that were not real numbers. So this theorem is telling us something important. As soon as we know that the matrix that we are studying is Hermitian, we automatically know that its eigenvalues are real numbers. So I want to walk through the proof of this theorem because I think it's an interesting exercise in manipulating symbols. So how do we prove this theorem? Let's start by choosing a unit vector v in any one of the eigenspaces of this matrix S. So the idea, by writing v belongs to script e sub s lambda, what we are declaring is that v is an eigenvector of the matrix S, where the eigenvalue here is lambda. Our goal is to argue that lambda has to be a real number. So let's see how we can do this. Well, lambda is the same thing as lambda multiplied by the length of v squared, because we are told that v here is a unit vector. So the length of v is equal to 1. So this is a famous trick in math. Sometimes it's convenient to multiply whatever we're looking at by 1 in a convenient way. Well, what is the length of v squared? This is the same thing as the inner product of v with itself, and that's by definition. Well, one thing we know about inner products is that we can take scalars on the outside that we're multiplying an inner product by and move them into the second position without even conjugating that scalar. Now, we know that v is an eigenvector of the matrix S, where the eigenvalue is lambda. What this means is that lambda times v is the same thing as S times v. This is by virtue of the fact that v is an eigenvector, where the eigenvalue is lambda. And now one thing we've said about inner products is that if we have a matrix inside of an inner product on one side, we can always move it to the other side, but when we do, we have to conjugate transpose the matrix. So v inner product with S times v is the same thing as S star times v inner product with v. Well, what do we know about the matrix S that we are studying in this situation? We know that S here is a Hermitian matrix, which means that S star is actually equal to S. So S star times V is really the same thing as S times V, because S star equals S. And we already know that S times V is the same thing as lambda times V, again because V is an eigenvector of S, where lambda is the eigenvalue. And now we know that we can always factor out scalars from the first part of an inner product, but when we do, we have to conjugate that scalar. So now lambda times v inner product with v is the same thing as the conjugate of lambda multiplied by the inner product of v with itself. Well, we already know that the inner product of v with itself, by definition, is the length of v squared, and we said from the very beginning that the length of v, that v was chosen so that its length is equal to 1. So this quantity is equal to the conjugate of lambda. So in our calculations here, we have lots of equalities, but the very first thing we wrote down was lambda, and the very last thing we wrote down was the conjugate of lambda. So we have successfully argued that if lambda is any eigenvalue of a Hermitian matrix called S, then lambda must equal its own conjugate, but the only numbers that equal their own conjugates are the real numbers. So this successfully argues that lambda had to be a real number to begin with. So this concludes the proof of the first part of the spectral theorem, which says that the eigenvalues of any Hermitian matrix are guaranteed to be real numbers. So what sorts of things can we do with this information? Well, for one, we can immediately conclude that the eigenvalues of all three of these matrices are guaranteed to be real numbers without even looking at what those numbers actually are. So the eigenvalues of each one of these three matrices are real because each one of these three matrices is Hermitian. The first two of these three matrices are real symmetric matrices, and real symmetric matrices are always Hermitian. And the last of these three matrices is not real symmetric, but it is Hermitian. So as soon as we know the matrix we're studying is Hermitian, which means that the matrix might be real symmetric, or it might have non-real entries but be Hermitian, we automatically know that the eigenvalues, whatever they are guaranteed to be real numbers.